My name is Willis, and I am in the Department of Natural Sciences at Marshall University. My mentor on this research project was Dr. Gilly, and today we'll be talking about the effects of anthropogenic light emissions on bats in Southern Appalachia. So first, I wanted to point out some of the aspects that highlight the significance of this study. The first being that bats that forage in open areas around lights are presumably more susceptible to predation by owls. However, certain species have adapted to forage around streetlights. This includes the eastern red bat, which is a common bat in this area. The idea is that a light source attracts insects, causing an abundance of prey in that area, or in other words, a concentrated food source. Another issue is white nose syndrome, which is a fungal growth on the muzzles of bats that has caused large population declines in many species. So it's imperative that conservation measures find additional means to support local bat populations. The reasoning behind conducting this research can be attributed to some of the questions that arose before the early stages of designing my experiment. This includes how humans are impacting local bat species, whether or not urbanization is a good thing, and finally, which species are typically found closer to lights. All of these would soon become the focus of my research. The artificial light that is emitted from cities can disrupt natural patterns among nocturnal species. Whether this disruption is positive or negative is species-specific. Insects are attracted to light. Thus, an insectivorous bat would presumably be more active around lights when foraging for food. However, studies have shown that not all insectivorous bats react the same to an artificial light disruption due to the higher importance of other environmental factors when foraging. For instance, the common bent-winged bat is more influenced by humidity and proximity to a roost. The higher priority of these factors suggests that the common bent-winged bat will not have a positive or negative reaction to light disruption. They will only experience this reaction if the percent of humidity or proximity to a roost changes. However, the same can't be said for all bat species across the taxa. Another factor is the type of light that is used in cities. For instance, a mercury vapor lamp produces a higher level of ultraviolet radiation that highly attracts insects, whereas LED lights emitting a lower level of ultraviolet light attracts less insects. This change in prey abundance may affect varying species differently, thus implying that conservation efforts regarding city lights would be dependent on the local bat species. Alright, so here are some visuals of some of the bat species that we recorded on the transects. This one in the upper left corner that is in the middle of aerial hawking an insect is the Mexican free-tailed bat, Turdurita brasiliensis. It is a narrow-winged bat. The one down in the middle is the hoary bat, Lacerius cinereus. It's a broad-winged bat. And the one pictured in the upper right-hand corner is the Indiana bat, Myotis sodalis. It's a broad-winged bat. Now, this bat is actually marked as endangered currently, so conservation efforts on this species need to be prioritized. The question we were trying to answer with this experiment is, do light emissions from cities cause a statistically significant difference in bat foraging behaviors? Based off this, we formulated the hypothesis that as the amount of light emission increases, the foraging behaviors of eastern red bats and narrow-winged bats will increase, while foraging behaviors of all other species will decrease. Further contemplation on this hypothesis led to 3 predictions. Those include the biodiversity of bats foraging will decrease closer to city limits due to light emissions and less suitable forested habitat. The second is that the number of eastern red bats and other narrow-winged bats foraging will increase closer to city limits due to increased prey availability. And the third and last is the diversity and number of broad-winged bats that are not adapted to forage near lights will decrease closer to the city due to increased predation risks. In this study, bat vocalizations were recorded using Anabat Swift bat detectors, pictured to your right, in 3 study locations: Pickens, South Carolina, Mars Hill, North Carolina, and Weaverville, North Carolina. All surveys follow the North American Bat Monitoring Protocol, which was released in 2015. Recorded vocalizations were analyzed using the Wildlife Acoustics Kaleidoscope software and manually vetted by Dr. Gilly to determine the species. Data collection included the total number of bat vocalizations and number of each species recorded for the 3 study areas on each transect. In order to collect data at the 3 research areas, global positioning systems were used during the duration of each drive. The bat vocalizations were captured by mounting the Anabat Swift acoustic detectors to the top of a vehicle with their microphone facing upward, and this was done during a sampling period from August to October in 2020. 2 different statistical tests were run on the data to determine significance, the Mann-Whitney U-test and the median test. The results of these will be discussed later in the PowerPoint. These are the maps depicting the transects used for acoustic surveys with the urban city at the center. As you can see, in each transect there is a blue pinpoint that denotes the city center. We concluded that this point would have the highest light emission. The goal of each of the 2 transects per study site was to drive directly outward from the city center for 5 kilometers, or 6.2 miles. Another issue to take note of in this experiment is when driving 5 kilometers outward from the city center doesn't account for a coherent 5-kilometer radius from the city center because certain roads are curvier than others. Total bats recorded in the study was 26. The total species recorded was 8. The total number of broad-winged bats was 20, and the total number of narrow-winged bats were 6. In relation to the hypothesis, the foraging behaviors of eastern red bats and narrow-winged bats will increase while foraging behaviors of all other bats will decrease, the null is retained. There is no significant difference between the species that were found closer to city lights compared to further away. 2 statistical tests were ran on this data, the Mann-Whitney U-test and the median test. Within the Mann-Whitney U-test, the total N was 12, the standard error was 6.223, and the p-value was 0.485. I've inserted a picture in the lower left-hand corner of what a bat call looks like. This is an example of some data we would use for species identification. This specific picture is the hoary bat. This image is called a spectrogram, which is just a visual way of representing the bat call. These are 2 graphs I configured to simply represent our data in a more aesthetic manner. The chart to the left represents our detected bat species. As you can see, the big brown bat had 8. The northern yellow bat had 1. The hoary bat had 2. The silver-haired bat had 4. The tricolored bat had 6. The evening bat had 3. The Mexican free-tailed bat, that is the Tatarita brasiliensis, had 1. And lastly, the Myota sudalis, the Indiana bat, had 1 as well. Now the other side to the right, the wing morphology of the detected species is simply put, there was 20 broad-winged bats and 6 narrow-winged bats. The narrow made up 23% of the data, while the broad made up 77% of our data. Now, these 2 graphs were configured from the 2 statistical tests that we ran, the Mann-Whitney U-test and the median test. And to your left on the median test, this is a standard box plot, and you can see by the standard error bars that we did not have statistical significance, and in fact the p-value is listed as 1.0, which is way over. But if you look to the right at the Mann-Whitney U-test, this is what's displaying a trend that more bats were found outside of the first 2.5 kilometers. However, we didn't get statistical significance on this trend because the p-value on this chart was 0.485. Now just to go through some explanations of this Mann-Whitney U-test, the right side is after 2.5 kilometers, while the left side, the lighter blue, is before 2.5 kilometers, which coincidentally would be closer to the city center. And as for the x-axis of frequency, the test pretty much denoted any pulses, the y-axis of bat activity, that's from -20 to 80, that's the pulses. Any pulses from 20 to 40, it denoted as a frequency of 1. So because of this, you can see this outlier that we discovered at a pulse from 60 to 80 as a frequency of 1. Now that frequency of 1 essentially means that there was only 1 occurrence in the data where this happened. Because of that, we didn't get statistical significance in saying that more bats occurred outside of 2.5 kilometers. After excluding calls that were unidentifiable due to low pulses recorded before or after the official transect, or were later manually identified to be flying squirrels, because yes, we did get some that were posing as bats on the detectors, There were 26 bats recorded, and this ranged over 8 species, which ironically didn't include the eastern red bat, one of the most common bat species in Appalachia. Now, while the data did not display a statistical significance that supported our hypothesis, there was another trend that I previously talked about from the Mann-Whitney U-test. More bat species were recorded after the first 2.5 kilometers, which suggests that there are a limited number of species that are adapted to forage near the city lights. This trend that we observed in the data could explain the higher number of broad-winged bats that we got versus narrow-winged due to their tendency to prefer a rural setting. This is because they fly slower, have less maneuverability, and prefer to glean their prey. Because of this trend, we suggest that our data was tested non-significant because the sample size was simply too small. However, other factors could also be coming into play, including larger towns with more light emission and less habitat may change results, or the time of sampling that we did could have affected the species that I recorded. Or lastly, the sampling season that we had to record in, which was August to October due to COVID rules, could have also affected our test of significance. So some things I learned from a purely experience standpoint is that trial and error is present every step of designing an experiment and conducting it. Patience and cooperation is key, especially cooperation with my mentor, Dr. Gilly, well, your mentor, whoever that may be, and the people that were helping me on the transects, which includes Emily Winmouth, Eleanor Dunlap, and a friend from home, Jordan Sutter. Improvements in technology can always be made. We didn't always have detectors that could pick up these bat calls, and we didn't always have kaleidoscope that could offer us a spectrogram to visually view them. And some things I learned from the results of my research itself was that my hypothesis could possibly be accepted one day if those alternative reasons for the test of non-significance are addressed. And lastly, I'm sure you've noticed in this PowerPoint that I've said it a few times, something that is common doesn't mean it's certain, as in, I'll say it again, the eastern red bat is one of the most common species in Southern Appalachia, and I didn't record any. So that goes without saying, if you have a question in science that you think is already answered, you should still probably run a test on it because you never know what you're going to get. These are my citations, and thank you for listening to my presentation on the effects of anthropogenic light pollution on bat species in Southern Appalachia.